Let's see the application of permeability, which is a very important aspect in all geotechnical engineering. Just to give you a simple example, you have a large earth dam. You are building with some coarse material and a fine-grained material which will prevent. Earth dam has to have two components, a strong material to make it stable and a very fine-grained material which is impervious, which will not allow the water. Because the other components are, it has a protection in terms of riprap, and then if you want to prevent flow through the foundation, we provide a cutoff too, so that no water will leak either through the dam or through the foundation. If you have a concrete dam, again we have similar problem. This is a solid concrete dam or a barrage or a weir, and there will be no flow because these materials have very low coefficient of permeability. But the flow can take place through the foundation, and we have to be very careful about it. So here again you can see the datum is fixed somewhere here, and this is the height or the head loss. The water level here on this side is at a height h with respect to the datum, and the water level at the downstream side is at the datum level. So when we see the later, we talk of this as the head loss. If we don't do a proper job, we have several disasters. One of the very famous one is called Baldwin's Hill Dam in USA. Because of the leakage, the soil got washed away and the whole dam failed. As you can read through this, and this erosion is the cause of failure for this Baldwin Dam. Similarly, we have another major piping failure where the dam is solid concrete, but the soil below the dam got washed away, which is a phenomenon called piping. We'll talk of that in the next module when we look at seepage and exit gradient. The problem again here, if you do not take care of the flow, you can have serious problems. Similarly, if you have a retaining wall, you have a retaining wall here, the ground level on one side and the other side, you have to provide what they call as weep holes so that the water can escape. If they don't do it, the water gets collected and the retaining wall will fail. So we try to make use of several alternatives. We provide a granular fill, we collect the water through a pipe, or we provide a geosynthetic either here or at the face of the wall. And you need to work out how much water will be collected here. So let's come to the basics of flow through soil. As I said, we need the total head, which is consisting of pressure head, elevation head, and they add up to this. Because the velocity head, according to which law? We know the velocity head is so negligible. Normally the velocity through soil is very, very small, some order of less than a meter per minute. So when I'm trying to calculate the head, it is something like 10 to the power minus 6. So we neglect the velocity head. Just to give you an idea, here is a bucket of water, level 1, point 1 and point 2. The pressure here at 2 is more. As you can see, if I put a standpipe, the water level will rise up to here. So the pressure head is more at point 2 than at point 1. But the elevation head of point 1 is more than the elevation head of point 2. So you can see here, if I look at the top and the bottom, the total head is the same, but the elevation head increases as you go to the top and the pressure head decreases. But the sum of those two remain constant, and because of which there will be no flow. So this is what happens. And if you are looking above the water table, the elevation head increases, but the pressure head decreases, and that is what we call as capillarity, wherein the pressure inside the tube is negative. The sum of these two will be equal to 0. So if the elevation is positive, the pressure head has to be negative. So in the soil above the groundwater level, you will have negative pore water pressure, which we call capillarity, and the maximum it can rise depends on the void space. And you know that the flow will take place through the soil. If I have a loose soil, you can see there is more facility for it to go horizontally. The flow is easy and you will have higher permeability. If the soil is dense, obviously the void spaces are small and it's very tortuous. So you find that it's very difficult for flow, and also permeability is low. And we talked earlier about the directional dependence. Here the flow is high in the horizontal direction than in the vertical direction, whereas here the flow is very low in the horizontal direction. So permeability very less. So this is Bernoulli's equation we were talking earlier. Kinetic energy due to velocity, strain energy due to pressure, and potential energy due to elevation. This is what we neglect. So total head is sum of these two. Velocity head is 0, so we take only pressure head and elevation head. So if the flow is from point A to point B, there's going to be head loss. That difference is what causes flow. So if I look at total head at point A and total head at point B, I take the difference and find the distance between these 2 points A, B. I divide by the length AB. I get the gradient here. Darcy said that the velocity is proportional to the gradient, and the constant of proportionality is called the permeability, or technically we also call it as hydraulic conductivity. It's like electrical conductivity or thermal conductivity. To keep in similarity with other phenomena, we also call it hydraulic conductivity. The units are velocity, so V is centimeters per second, I is dimensionless, so K has to be also velocity. These are some of the values. Again, I mentioned to you the permeability is a function of fluid properties and intrinsic permeability, and this is unit weight of water, viscosity coefficient, and this is intrinsic permeability, which depends only on the soil characteristics. So if you want permeability at a standard temperature of 20 degrees, you determine in the lab and multiply by viscosity at the lab temperature divided by the coefficient of viscosity at 20 degrees. And you can see that viscosity ratio decreases with increasing temperature. So at 20 degrees, the ratio at any temperature by 20 is 1, but let's say you are looking at something like 25 degrees, the coefficient becomes 0.89. So we had to multiply the permeability at 20 degrees will be 0.89 times the permeability you have measured in the lab. The range of values are gravels more than 10, 10 to the power of 0 means 1 centimeter per second. Sands, they are more than 10 to the power of minus 3 centimeters per second. Silts are more than 10 to the power of minus 6, less than 10 to the power of minus 3 centimeters per second. And clays are all very, very impervious with 10 to the power of minus 6 centimeters per second or less. This is another way you can look at the same data.